on this question, we want to analyze the graph of the rational function r of x equals 5x plus 5 over 2x plus 4. And we're going to go through several steps in solving this problem. And the first step is to write this function as a single rational expression. And this is already like that. We have one fraction. And then we're going to factor the numerator and denominator. So our numerator has a common factor of 5. I can factor that 5 out to get 5 times x plus 1. And the denominator has a common factor of 2, so I can factor out the 2 to get x plus 2. So this rational function, written in factored form, I notice that it doesn't have any common factors. So it's already a reduced rational function. So next we're going to look at the domain of this rational function r of x. And with rational functions, we have one concern, and that is the denominator. The reason why the denominator is a concern is because dividing by 0 is undefined. So with rational expressions that have a variable in the denominator, you have that possibility of creating a 0 in the denominator. So to find the domain of the rational function, we're going to take the expression in the denominator, 2 times x plus 2, and we're going to set that equal to 0. I can get rid of that 2 by dividing by 2 on both sides. And I have x plus 2 equals 0. And subtract 2 on both sides, and that gives x equals -2. So this -2, we call this a restricted value, because that's going to cause the denominator to equal 0 and the expression to be undefined. We need to exclude this restricted value from the domain. Now there are two common ways of writing the domain, and that is in interval notation and also in set builder notation. So in interval notation, we would think of the real number line as -infinity to infinity, and then take that one value of -2 out of the set of real numbers. We're going to write that in two intervals, the interval to the left of -2 and the interval to the right. The interval to the left would be -infinity to -2. That's all the numbers that are less than -2. And the interval to the right would start with -2 and go to infinity. So this would be writing our domain in interval notation. Now with set builder notation, we write curly braces to indicate that we're talking about a set of numbers. And our domain are a set of x values. And those x values can be any real number except for -2. So we write this vertical bar. This vertical bar, we say it as such that, but behind the vertical bar are any conditions that we put on the numbers in the set. So we only have one rule, and that is that x cannot equal -2. Other than that, any other real number can be included in the set. So you can write the domain in interval notation as -infinity to -2, union with -2 to infinity, or you can write it in set builder notation as any real number not equal to -2. So the next thing that we're going to look at are the intercepts of the graph. We're going to look for x-intercepts and y-intercepts. Usually y-intercepts are a little bit easier to find, so we'll start with that. So to find a y-intercept, we're going to let x equal 0. I'll substitute a 0 into my function r of x. That will give 5 times 0 plus 5 over 2 times 0 plus 4. And that leaves me with 5 over 4. And so we have a y-intercept of 0, 5 over 4. Then I want to find the x-intercept. Find the x-intercept, I'm going to let y equal 0. And we don't have a y in the equation because we're using function notation. So we have to keep in mind that r of x is the same thing as y. So we're going to set r of x equals 0. That's going to give us the equation 0 equals 5x plus 5 over 2x plus 4. I'm going to solve this equation by multiplying both sides by the denominator. 2x plus 4 times 0 is 0. And on the right-hand side, multiplying by the denominator cancels out the denominator, leaving me with just 5x plus 5. And I can solve. I'm going to subtract 5 on both sides, giving me 5x equals negative 5. Divide both sides by 5, and I get 5 equals negative 1. So this function, this rational function, has an x-intercept at negative 1, 0. Now, when we studied polynomial functions, we learned about the behavior of x-intercepts. The graph can either cross or touch at the x-intercept. And we determine whether the graph crosses or touches by the multiplicity of that x-intercept, or that 0. So what we want to do is we want to determine the behavior of our x-intercept of negative 1. And we do that by taking a look at our rational function. So this rational function, remember, is r of x equal to 5x plus 5 over 2x plus 4. We wrote that in factored form as 5 times x plus 1 over 2 times x plus 2. And if we analyze this factor of x plus 1, this factor of x plus 1 is the factor that matches our x-intercept of negative 1. And this factor is only raised to the first power, so that means that that factor has a multiplicity of 1. And because that multiplicity is odd, we know that the graph will cross at that x-intercept. So we know that we have a factor of x plus 1, which has a 0 of negative 1. That 0 has a multiplicity of 1, and because it is an odd number, we know that our x-intercept will cross the x-axis. Our graph will cross the x-axis at that x-intercept. Okay, so now what we're going to do is we're going to look for vertical asymptotes. And when we look for vertical asymptotes, what we do is we keep in mind what we did earlier. So remember earlier we found the domain and we found a restricted value of x equals negative 2. That restricted value is either going to be a vertical asymptote or it's going to be a removable discontinuity. And in shorthand, we usually call these holes in the graph. So when we look at, and then I have this x plus 2 here, shouldn't be there. When we have our rational function in factored form, we can look to see that factor. This is the factor that produced the restricted value of -2. You're going to look to see if that has a common factor in the numerator. You're going to look to see if you have another factor of x plus 2. If you have another factor of x plus 2 in the numerator, you have a removable discontinuity. But if you don't, you have a vertical asymptote. So since our function doesn't have that common factor in the numerator, we know that there is a vertical asymptote at x equals -2. So now that we know that we have a vertical asymptote, we want to know what that looks like. What does that look like on the graph? So we want to determine the behavior of the graph on either side of that vertical asymptote. So when we're thinking about the behavior of a vertical asymptote, we want to keep in mind the definition of a vertical asymptote. With that definition, what we know is that as x approaches that asymptote, in our case, -2, we know that the y has two choices. Your y's will approach infinity, or your y will approach -infinity. So we really have four scenarios that could happen when we have a vertical asymptote. So you could have your vertical asymptote, let's say at -2, and on both sides they go to positive infinity. Or you could have your vertical asymptote at -2, and on both sides go to -infinity. Or you could have them going in opposite directions. So maybe the right goes to positive infinity and the left goes to -infinity. Or maybe the left goes to infinity and the right goes to -infinity. So these are the four choices, and we need to figure out which one is the behavior near our asymptote. So the way we do that is really just with a test value. So we have our rational function, 5x plus 5 over 2x plus 4. And we want to figure out the behavior around -2. I'm going to pick a test point on either side of -2, like -2.1 and -1.9, and that's going to tell me the behavior on either side. So let's test that. R of -2.1 would be 5 times -2.1 plus 5 over 2 times -2.1 plus 4. So I'm going to get my calculator. And I've got 5 times -2.1. It's going to be a -10.5 plus 5. And in the denominator, 2 times 2.1, -2.1, would be a -4.2 plus 4. And really the important part here is whether it comes out positive or negative. So we've got a negative in the numerator and a negative in the denominator, and negative divided by negative is positive. So now I know, because that came out positive, that on the left-hand side, I'm going to be approaching positive infinity. So then I'll check -1.9. So 5 times negative 1.9 plus 5 for 2 times negative 1.9 plus 4. That's 5 times negative 1.9. That will be a negative 9.5 plus 5. 2 times negative 1.9. That is a negative 3.8 plus 4. And this is going to be a negative over a positive, which gives me a negative. So I know on the other side, it's going to go to negative infinity. So on the right side, it goes to negative infinity. So we figured out that our behavior looks like this one right here. So for the next part, we're going to find the other type of asymptotes, horizontal or oblique asymptotes. And finding these horizontal or oblique asymptotes in an algebra class involves some memorizing of rules. The actual calculations involve an operation called limits, which is usually taught in a calculus class. So we're going to take this group of summarized rules that's been created for us to determine the asymptotes. So these rules involve the degree. So we need to know the degree of the numerator, which we usually call n. And the degree of this numerator, we have x to the first power, and so we have a degree of 1. This is the degree of the numerator. And then we need to know m, which is the degree of the denominator. And it also is 1, x to the first power. It's a degree of 1. We take the highest power if we have more than one variable there. And we compare them. And one of the comparisons involves them being equal to each other. I typically call this case 2, where n is equal to m. Anytime we have the degree of the numerator equal to the degree of the denominator, we are going to have a horizontal asymptote. And that horizontal asymptote is y equals the ratio of the leading coefficients. And the leading coefficients are these coefficients that are attached to the highest degree term. So the horizontal asymptote for this example is y equals 5 over 2. So we're going to have a horizontal asymptote at y equals 5 over 2. So the next part involves determining whether we have any points where the graph intersects the horizontal asymptote that we just found. So we want to find where the graph intersects or crosses the horizontal asymptote that we just found. So the graph we're referring to is the graph of 5x plus 5 over 2x plus 4. And the horizontal asymptote that we found is 5 over 2. And if they cross each other or intersect each other, that means they have to be equal to each other. So we can create this equation where you set the function equal to the asymptote that you just found, and that's going to tell you any points where they cross each other or where they equal each other. So I'll solve this equation. I'll do that with cross multiplication. So if we multiply 2 times 5x plus 5 equals 5 times 2x plus 4, we would get 10x plus 10 equals 10x plus 8. And as you solve this equation, the variables end up canceling each other out, and we get 10 equals 8. This is obviously false, and so that tells me that this is an equation with no solution. So for this particular example, the graph will not cross the horizontal asymptote. It does not cross or intersect the horizontal asymptote. So we're going to put all of this together in order to sketch the graph of our rational function. So I wrote down everything that we figured out. We have a vertical asymptote at x equals -2, a horizontal asymptote at y equals 5/2. We found both an x-intercept and y-intercept, and if you'll recall, we did find that our graph crosses at that x-intercept. We have a y-intercept at 0.5. We know the graph does not cross the horizontal asymptote. So we're going to take all that information and draw a sketch of this graph. So I'll start by putting in the asymptotes and the individual points that we found. So I'm going to make this really big. So let's make this -1 and -2. We have a vertical asymptote. I'll label it vertical asymptote at x equals -2. Then we have a horizontal asymptote at y equals 5/2. That's 2.5. The horizontal asymptote at y equals 2.5, or y equals 5/2. We have -1, 0 as an x-intercept, and 0 and 5/4. 5/4, that's going to be 1.25. So that'll be about right here. We also found that the graph will go to positive infinity on the left and negative infinity on the right. So we know that these 2 points will connect to each other, and on the right of that vertical asymptote, it will go to negative infinity. If we continue to follow this line, it should approach the horizontal asymptote by definition. And then we also know that the other side of the graph will be, or the other side of the asymptote will go to positive infinity. So this gives us a sketch of our rational function. So on this example, we are given this graph of a rational function, and we want to find the domain and range, the intercepts, horizontal asymptotes, vertical asymptotes, asymptotes. So starting with the domain and range, for domain, we're going to assume that the ends of these graphs continue on. So we're pretending like they have arrows and the lines continue on. And the dashed lines that you see on the screen are the asymptotes. And they indicate where the graph is approaching that line but not reaching the line. And so this function, this graph, will have a break at the asymptote of x equals -3 and another break at x equals 3. So I can kind of see, and I like to use a ruler if I'm not sure about it. And I'm going to hold my ruler vertically. And the reason why I hold it vertically is because it points to your x-axis. So if I go from left to right, I can see that all of these points on the x-axis are covered until we get to that vertical asymptote. What I mean by covered is that I'm touching the graph, and if I'm touching the graph, I'm also having an x value at that place on the x-axis. So it's covered all the way except for those two asymptotes. So I know that my domain is going to be all real numbers except for those two asymptotes. So you can write that in interval notation, or you can write it in set builder notation. If you write it in interval notation, that would be negative infinity to negative 3, union with negative 3 to 3, union with 3 to infinity. If you write it in set builder notation, we're talking about domain. So we're going to do a set of x's, and we want to exclude only 3 and negative 3. So it's all real numbers except for 3 and negative 3. For the range, we have this one horizontal asymptote, which is occurring at x equals negative 3. And we'll notice here that there's a gap in the y values. You could also use the ruler again and hold it horizontally. Horizontally because you're pointing at the y scale now, and range is the y values. So you can see that down here, my ruler is touching the graph, so that means that this graph has all of these y values below the horizontal asymptote. However, when we go above the horizontal asymptote, there's a little section right there that I've highlighted where I'm not touching the graph with the top part of my ruler. So for this group of y values, we have to exclude them from the range because we have no ordered pairs on this graph with those y values. And then from here on up, our ruler is touching the graph, and we have parts of our range included. So if we were to write our range, remember this is the domain, these first two, the range in interval notation would be negative infinity to negative 3, and then negative 2 to infinity. Now you'll notice that I have put a parenthesis on the negative 3. That's where the asymptote is. My graph never reaches that asymptote. It keeps getting closer and closer. However, I've put a bracket on the negative 2, and you can see, looking at this particular point on the graph, this is the ordered pair, 0, negative 2, and it's on the graph, so we would include that negative 2. If you were to write this in set builder notation, we would use the curly braces and use y, since we're talking about y values with the range. Below the horizontal asymptote, the y values are less than negative 3. And then above that horizontal asymptote, those are y values that are greater than or equal to negative 2. So we want y values that are less than negative 3 or y values that are greater than negative 2. So we found the domain and range. Now we want to find the intercepts of this graph. So I'm going to get rid of all my markings so it's a little bit easier to see. And you can see that we do have some x-intercepts here and a y-intercept here. We already listed out that y-intercept as 0, -2. And the x-intercept is a little bit hard to read from this graph because we have all these extra tick marks. So I need to figure out what the value of a tick mark is before I can figure out what those x-intercepts are. So what I'm going to do is just look at one set of tick marks. Let's go from 0 to 1 here. And let's count how many spaces we have. We have 1 space, 2 space, 3 space, 4, then 5. So we have 5 spaces in between 0 and 1. So we can think of these as each fractions. This is 1 out of 5, which is 0.2. This is 2 out of 5, which is 0.4. 3 out of 5 would be 0.6. 4 out of 5 would be 0.4, and 5 out of 5 would give me 1. So that's how we need to think about those tick marks. So let's see if we can figure this out. We've got our x-intercept here. I'm going to erase that so we can see the tick mark. So we've got 1 tick mark, 2 tick marks below. So that's going to be a -2.4. And this one on the right-hand side will be 2 tick marks above. So that's going to be 2.4. So we have intercepts -2.40, 2.40, and 0, -2. So now we're going to look for horizontal asymptotes, vertical asymptotes, and oblique asymptotes. And we really had to already find them to understand what the domain and range were. So we located a horizontal asymptote at y equals -3. So that is part C. Y equals -3 is the horizontal asymptote. Vertical asymptotes, we had 2 of them at -3 and 3. And that's x equals 3, x equals -3. And for part E, asking about oblique asymptotes, an oblique asymptote would be a slanted line, and we don't have any slanted asymptotes here. So we have no oblique asymptote for this example. On this question, we want to find the center, the transverse axis, the vertices, foci, and asymptotes, and then also graph the equation. We have an equation of a hyperbola here, x squared over 81 minus y squared over 64 equals 1. So I knew this was a hyperbola because it had that minus in the equation. So what I like to do first is to figure out the orientation of this hyperbola. So the orientation is either going to be horizontal or vertical. And the way that you can tell whether it's going to be horizontal or vertical is by paying attention to which term, which variable, I guess, is positive and which one is negative. So you'll notice here in the horizontal orientation that your x term is positive and your y term is negative. However, in the vertical orientation, this is a typo here, this should be a minus, your y term is positive and your x term is negative. So this is a typo that I have in my notes. That should be a minus. So looking at our example, we have x squared over 81 being positive and the y squared over 64 being negative. So we can tell that our hyperbola is going to have a horizontal orientation. Now that's important because that tells us a lot about our hyperbola. Having a horizontal orientation tells us that our important features are all going to line up horizontally. And they line up horizontally along this transverse axis. So this is going to be our transverse axis. It's horizontal. You're going to have the center. Around it you have vertices, and then around that you have your foci. So you have the center, vertices, and foci. Now at this point I can already tell what the center is. The center is going to be HK, and in my equation I don't have anything added or subtracted, so I can tell that the center is going to be at the origin 0, 0. Now then I need to find the vertices and the foci, and the way that I find that is using the values of A and B. So we have in the denominator here values of A and B. Now A is going to be the distance between the center and the vertices. So that's this distance here. And C is the distance between the center and the foci. B is a little bit harder to show on this graph, but it has to do with the asymptotes that show where these parts of the graph go. So I'll try to show you that a little bit later. So I know in my equation A is always going to be underneath your positive term. So I can use this 81 here to figure out what A is. I know that A squared is 81, so that means that A is going to be 9. So I know that if I move to the left and to the right of my center, I'm going to get to my vertices. So I'm going to have vertices at negative 9, 0 and 9, 0 because I found that value of A. I found the center and the vertices. The transverse axis passes through the center, and we already said it's horizontal. So we know that the transverse axis is going to be the line y equals 0. I can find the foci with the value of C. I don't know the value of C yet, but I can use this equation here to figure out that value of C. I know that B squared is going to be 64, so B has got to be 8. So then I'll use this equation, A squared plus B squared equals C squared. 9 squared plus 8 squared equals c squared. 81 plus 64 is c squared. And that is at 165, 155, 145. Now, is that a nice square root? No. So c is equal to the square root of 145. And I can find my foci using my center. So from the center, I'm going to move left and right the amount of that foci. So we have negative square root of 145, comma 0, and negative and positive square root of 145, comma 0. So we found the foci and the asymptotes. So your asymptotes are going to be right here. So as I was saying earlier, the value of b is a little bit hard to see on the graph. But if we take the value of b coming off of our vertex, it creates this diagonal going through the center, and that's going to guide us on where to draw our arrows here at the end, where the end behavior of this graph is headed. So visually, that's what b represents. So you can see in our equation for the asymptotes, b is used as the slope. B over A is the slope. That's our rise over run. So our asymptote is going to be y minus k equals plus and minus b over a times x minus h. That's y minus 0. Remember, our center is at 0, 0. B is 8. A is 9. So we have plus and minus 8 over 9. And x minus 0. So simplifying that, we get that our asymptotes are y equals plus and minus 8/9 x. So let me just zoom out a little bit so you can see everything that we worked on there. Okay, it does want us to graph the equation. We have our center at 0, 0. If I go 9 to the left, that's going to get to a vertex 9 to the right. Another vertex. I'm going to count up by 8. That's going to help me to mark out where the asymptotes are. I'll go down by 8. That's the value of b. And this guides me to draw the hyperbolas following those asymptotes. In this example, we want to find an equation for the hyperbola described, graph the equation, and this particular hyperbola will have a center at 0, 0, a focus at 7, 0, and a vertex at 1, 0. So the first thing I like to do is to figure out the orientation. So I'm going to draw a little sketch of the information that I've been given. So I was given that I have a center at 0, 0, and a focus at 7, 0, and a vertex at 1, 0. So I can see that these 3 points are lining up horizontally. So I know that I'm going to have a horizontal transverse axis. That transverse axis does contain the important points of the center, the vertex, and the focus. So I know that the basic equation that I'm going to use is this one here. In order to fill that equation, I need to know the h and k. The h and k, h comma k is the center of the circle. I also need to know a and b. So a is the distance between the center and the vertex. So I already have some of this information. I was given the center, so I know that center is the HK, and the distance between the center and the vertex is 1 unit, so I know that A is equal to 1. I don't know the value of B. We weren't given that information, enough information to figure that out. But I do have enough information to figure out C. C is the distance between the center and the focus. So I've got my focus right here, and the distance between that center and the focus is 7 units. So I know that C is equal to 7. So because I know C and I know A, I can solve for that missing value of B that I don't have. So let's solve that equation. A squared plus B squared equals C squared. 1 squared plus B squared equals 7 squared. So I have 1 plus B squared equals 49. I'll subtract 1 and get B squared is equal to 48. And if I square root both sides, I have B equaling the square root of 48. We can simplify this as well to get, I think 48 is 16 times 3, so we can write this as 4 square root of 3. So now that I know H, K, A, and B, I can write out the equation. And that's the first part of this problem, is finding the equation that has these properties. So I'm using the equation x minus h squared over a squared minus y minus k squared over b squared equals 1. We have x minus 0 squared over 1 squared minus y minus 0 squared over square root of 48 squared. And if we simplify, this will give us x squared over 1 minus y squared over 48, because the square root and the square cancel each other out. And we don't typically write divided by 1, so really we would write this as x squared minus y squared over 48 equals 1. So I've got the equation of that hyperbola, and it wanted me to graph it. I was writing down some of the details right here, but let's get a clear picture of our graph. I've got a blank grid here for us to fill out. And I'm going to go ahead and draw that graph out. So this is stuff we were given. We were given the center, and we were given a focus of 7. We were given a vertex at 1, 0. And because of this symmetry of the hyperbola, we'll have a mirror image on the other side. So I'll have another vertex at -1, 0. And I'll have another focus at -7, 0. And then if you'll remember, the asymptotes are going to pass through the center, and they're going to have a slope of b over a, actually plus and minus b over a. So we saw that b was the square root of 48 and a was 1. So let me approximate square root of 48. I'm just going to punch that in my calculator real quick. Square root of 48 is almost 7. So we're going to say this is almost 7, plus and minus 7. So I'm going to go up 7 and down 7. And this is going to give me my rise over run. So I rise almost 7, run 1, fall -7 and 1. This is going to give me my asymptotes for the graph. And those asymptotes tell me how wide to draw. So I'm going to start from these vertices and go straight towards following those asymptotes. So this hyperbola is very wide. So we have a sketch of our parabola there. Excuse me, I said parabola, it's a hyperbola. So in this example, we have the graph of a hyperbola given on the right, and our goal is to match it to one of these equations over here. So in order to do that, we need to figure out the orientation of our hyperbola and then maybe a little bit more information on top of that. So the hyperbola can be oriented horizontally or vertically. So what I'm noticing here is that we have the center of the hyperbola here, and then we have vertices of our hyperbola right here, and these points are lined up horizontally. So we have a horizontal transverse axis. So when we have a horizontal transverse axis, that means that our equation is going to follow the format of having the x term be positive. So we typically have x minus h squared over a squared minus y minus k squared over b squared equals 1. So when we have a horizontal transverse axis, this x term is going to be positive. If it were a vertical transverse axis, the y term would be positive. So you can see here, I can eliminate 2 of the equations based on the orientation alone. So this has the y term being positive, That's the equation of a hyperbola with a vertical transverse axis. Here's an equation with the y term positive. This has a vertical transverse axis. So that narrows it down to two of the equations. So the value of A in our equation visually on this graph is the distance between center and the vertex. So we have the center and the vertex, and they're 1 unit away. So I know that the value of A is going to equal 1. And so I know what's going to go underneath my x term is going to be 1 squared, A squared. So on this one I have 25, and on this one I have nothing, which is dividing by a 1. So now I know that this must be the right answer, and this one we can eliminate. So the equation of this hyperbola is x squared minus y squared over 25 equals 1. For this example, we want to find the equation of the ellipse, and we want to graph that equation using some facts about the ellipse. We have a center at 0, 0, a focus at 15, 0, and a vertex at negative 17, 0. So what I like to do first is to try to figure out whether my ellipse has a horizontal major axis or a vertical major axis. This is the orientation of the ellipse. So when you have a horizontal orientation, your ellipse will be longer horizontally, and all the major features will fall in line horizontally. When you have a vertical major axis, your ellipse will be longer vertically, and all of those major features will line up vertically. So I'll do a quick sketch of what I have here. I have a center at 0, 0, a focus at 15, 0, and a vertex at negative 17, 0. And because these points are all lined up horizontally, I know that this ellipse has a horizontal major axis, is oriented horizontally. So all of these points are lined up horizontally. So I know that my major axis is horizontal. So in order to find that equation, I need to find the center, HK, which was already given to me. I need to find A. A is the distance between the center and the vertex. So I have the center and I have the vertex. So I already know that A is 17. I need to know B, that B is the distance between the center and the minor axis. So it goes, instead of horizontally, it's going to go vertically, and I don't have that information. But I do have information about C. C is the distance between the center and the focus. So I have the center and I have the focus, so I know that C is 15. And I can use this equation to figure out the value of B, my missing information. So B squared plus C squared is A squared. B squared plus 15 squared is equal to 17 squared. So 15 squared, I think, is 225. And 17 squared is 289. I'll subtract 225 from both sides and get 64 equals b squared. So that means b is 8. So now I have all of the information to fill in the equation of my ellipse. It's x minus 0 squared over 17 squared plus y minus 0 squared over 8 squared equals 1. We'll do a little cleaning up and get x squared over 289 plus y squared over 64 equals 1. So we have the equation of our ellipse, and let's take a moment to sketch the graph of this ellipse. So I have a blank graph over here. And I'm going to count by fives instead of doing all the tick marks here. So horizontally, I'm going to go 5, 10, 15. And vertically, we'll do 5, 10, 15, 20. So I have my center at 0, 0. I have a vertex at negative 17 and positive 17. So this is 15, 16, 17 would be about here. Then because B is 8, I'm going to go vertically 8, so just below the 10. And we can sketch the graph of our ellipse using those points.
Thank you for checking out my videos. Have a great day.